All right, let's get started for today. Today's lecture, we're going to continue talking about light and optics. Last time we kind of introduced a little bit of the concept about light. What is light actually, fundamentally? And we said that the light was electromagnetic radiation, which means light is basically a manifestation of a wave propagating through space, propagating through whatever the medium is. And what is waving or what is oscillating is the electric fields and magnetic fields. And one of the interesting parts of it is that it's always an electric field and a magnetic field that are perpendicular to each other. And the direction of motion is always perpendicular to those two oscillations. And so what I mean by that is if you have light, then what you have is an electric field oscillating, let's say, up and down. Okay, and you have a magnetic field oscillating back and forth. So they're perpendicular to each other. And not only are they perpendicular to each other, but notice that if the wave is moving left to right, then those two waves are also perpendicular to the direction of motion. And this is what's called a transverse wave. Oops, transverse wave. A transverse wave is defined basically as a wave. Doesn't matter what type of wave it is. It could be a water wave. It could be a light wave, whatever. It's a wave where whatever the thing that is waving is, it waves in a direction opposite or perpendicular to the direction of motion. This is as opposed to what's called a longitudinal wave. Longitudinal. Which you can guess based on the definition of the transverse wave, the direction of motion is the same direction as the direction of the wave. And this is, it's a little harder to draw, but we're going to imagine sound waves are longitudinal waves. Okay. And so what a longitudinal wave is if the wave is moving left to right, then the waviness of the wave is also left to right. And so you can imagine having a bunch of air molecules and the wave is kind of the pressure moving the air molecules towards each other and away from each other. So you get like clumps and then it spreads out and then it clumps together and spreads out as the wave moves towards you. And that's what a sound wave is. Your vocal cords vibrate the air molecules as you push the sound out of your face, basically. And that pressure pushes the air molecules in front of your mouth towards the direction that you're speaking. And so it pushes the air molecules towards that direction, and then they relax and come back to the place they were. But that pressure continues to move in the direction you were speaking. And so those further down the line, those air molecules get pushed and then come back and get pushed and come back and so forth, so that you have the direction of motion of the wave, also the direction where the waviness is occurring. In other words, when you speak, let's say you're speaking to your friend, the air molecules that are vibrating are not vibrating up and down, they're vibrating towards your friend and back towards you. And so those are the two types of waves. Light waves, water waves, waves on a string, like if you have a jump rope and you have, one person holding a jump rope over here, one person holding it over here, and you kind of flick it like a whip, the wave travels from one point to the other, but notice that the string or the jump rope or whatever it is moving up and down. again, perpendicular to the direction of the wave. Longitudinal, that's more like sound waves. Sound waves are longitudinal. But of course, we're talking about light, so we're thinking of transverse waves. And again, what makes light unique is what is waving is not the particles of the medium. Like sound waves, what's waving is the air molecules that you're speaking into. And it's through the air that the sound is moving. That's why in space, if you're in truly empty space and you try to talk, there's no sound because you're not able to push or pressurize any molecules. And so there's nothing for the sound wave, quote unquote, to propagate through. But in, let's say, water waves, obviously it's the water molecules that are the waving thing. And so the water wave propagates through water. And so it's the medium, the water, that's waving. And a string, well, the wave is moving through the string. So it's the molecules of the string that's waving. Light is weird. Light can go through all these materials. You could pass light through water. You could pass light through air. Certain types of light can go through metals, can go through glass, can go through wood, all sorts of stuff. But it's not those materials that are waving. It's not like when you shine light through the air that the air molecules are vibrating, but rather it's the electric and magnetic fields that propagate throughout all of the universe. Those are the things that are waving. And so that's kind of a unique thing about light. Makes light special. All right, well, that's fine. So light, electromagnetic waves, that is, it's electric and magnetic fields that are oscillating as the wave propagates through space. That's what creates light. Now, the physical characteristics are some of the things we want to start to discuss. First of all, I already told you that the speed of light, how fast the wave of light moves, is called the speed of light, obviously. It's a very obvious name. And the variable we use for it is c instead of v. V is velocity. And anytime we talk about a wave, a speed of the wave, we always call it v for velocity. But since light is very special, we replace the v for velocity with c, a very special variable. But it just means the speed of light. And we know that the number we're going to be using is going to be 3 times 10 to the 8th. It's not exactly, I mean, what would be the chances that in this universe, God created light to move at a nice round number of 3 meters per second, whatever a meter is and a second is. So obviously there's an actual decimal representation. It's not an exact number, but this is close because it's really more like 2.98 times 10 to the 8th. But we're going to use 3 just to make it easier on the math. So 3 times 10 to the 8th meters per second. That's how fast light moves. And it always moves at this speed no matter what. As long, and when I say this, it's very important to understand that I don't mean that no matter what medium you're in, light is always at this speed. What I mean is, when you measure the speed of light in a medium, so let's say we're out in space and we're measuring it through a vacuum, we always get this number 3 times 10 to the 8th. But if we're in water, let's say we're in a swimming pool, and someone shines a laser pointer into the swimming pool. If I were to measure the speed of inside the swimming pool, well, it's not going to be 3 times 10 to the 8th anymore. It's going to be something different. Maybe it'll be 1 times 10 to the 8th, or 2 times 10 to the 8th, or something. It's a different number. But when I'm in the water, I will always measure the speed of light in water. It'll always be that particular number. Okay, so the speed of light changes if it's in a different material. If light goes through glass, it doesn't move at the same speed as if it was in air, because glass is more dense. It's harder to get through, let's say. Or water, again, at a different speed while it's in the water. But while it's in the water, it's always at the speed of light in water. That number will never change. Now, speed of light is c. 3 times 10 to the 8th. And when I say this number, this is in air or in a vacuum more particularly, but we'll count air as the same as vacuum. It's close enough. But that's not the only important characteristic about light. Yeah, it has a special speed and it always moves at this speed, fine. But there are other things too. For instance, the fact that when you look at things, light, there's different colors. Sometimes you see red light, sometimes you see blue light, sometimes yellow, sometimes white. And then, of course, you have other types of light I've already mentioned, which are things like radio waves or microwaves or X-rays. Those are all forms of light. They're all the same thing. They're not made of different things. They're all light. So what is it that makes some light look red and some light look blue? Well, I can't really answer it too well, but there are 2 other characteristics which define what's called the color of light. Okay, the first one is called the frequency, and that's little f for frequency. The units of frequency is 1/seconds. Okay. Now, we don't like to use 1/seconds as a unit. It's kind of a weird unit. So we replace it with a new symbol and a new name, but it means 1/seconds. And a new symbol is capital H and little z, which means hertz. Okay. So when someone says, what's the frequency of red light? Then you can say, oh, it's, 4 times 10 to the 15th hertz or whatever it happens to be. That's a fake number. But hertz is the unit for frequency. Okay. And hertz is 1/seconds. Now, what does it represent? What is frequency? Well, frequency, since what we have here is a wave, something oscillating, and I'm going to define the oscillation to be up and down just to give us a direction. When you have a wave that's oscillating up and down, like this, as it moves to the right, well, you could say, okay, if I count how many times the wave oscillates up and down in 1 second, that's what's called the frequency. So it's like the number of oscillations or the number of waves per second. And that's where the 1/seconds comes from, per second. Because number of oscillations, well, number is not a thing. So there's no unit for number of oscillations. So that's why it's 1/seconds instead of like, meters over seconds. Number of oscillations per second, that's a hertz. And so if you have this wave, you say, okay, here's 0 seconds, 1 second, 2 second, 3 second, like this. And you say, okay, this particular wave does 2 oscillations in 1 second, let's say. Well, then the frequency is 2 hertz. It does 2 oscillations per second. That's what frequency is. So that's the first or second characteristic. We have the speed of the wave, and we have the frequency. Now, everything I'm talking about here, although I'm talking in the aspect of light, also counts for all waves. Any wave I may talk about, if I could be talking about water waves or waves on a string, whatever, all waves have these characteristics. All waves has a certain speed. So like sound, a sound wave has a speed. And when you're in the air, sound traveling through the air always travels at a certain speed. And when it's in the water, it travels at a different speed. Sound traveling through metal has a different speed, but it always has a certain speed depending on what it's moving through. Same thing with frequency. All waves have a frequency. So although I'm talking about light, that doesn't mean these things are only for light. These things are for all types of waves. The other characteristic we want is called lambda. That's a Greek letter lambda. And it's called the wavelength, sorry. I kept thinking of a quantum mechanics term, wave function, wavelength. Okay. So this is our third physical characteristic about a wave, the wavelength. The unit is, of course, meters, because we're talking about a length. How big is the wave? How long is the wave, let's say? And so it doesn't have a fancy unit. It's just meters, wavelength. And what is it? Well, same kind of a thing as frequency. If we have a wave, here's our wave. And now, instead of this being a graph of time, this is a graph of distance, okay? And so this is like, where is the wave at, in distance terms? The wavelength is how long or how far does a wave go before repeating itself? And so if the wave starts here, it goes to here in one whole oscillation. So that this distance from here to here is called the wavelength of this wave. Kind of similar to frequency. Frequency is in 1 second, how many oscillations are there? Wavelength is or how far does the wave go in making one oscillation? Okay. Now these things are obviously related. If you have a very high frequency, that is to say something is moving up and down very, very quickly as it moves to the right, then you would imagine it's going to have a very small wavelength. Because if it moves, for instance, here's an example, as I move to the right, if I oscillate very quickly versus if I oscillate very slowly, well, the very quick oscillation, the thing with a high frequency, it oscillates very much. Obviously, the distance between waves is very small because it oscillated up and down in a very short period of time. Whereas if the frequency is very low, it takes a long time to oscillate, then it's going to move a lot further in doing an oscillation. And so the wavelength is very long. And so we see frequency and wavelength are related to each other. The higher your frequency, the lower your wavelength. And vice versa. If you have a very small frequency, so it's, there's only, 2 oscillations per second, then the wave can move a bigger distance before it makes another oscillation. And so a small frequency means a very long wavelength. But what exactly is the relationship? I mean, obviously, when we do science, it's good to have a conceptual view, but we also want the mathematical to be able to do calculations. And the actual relationship in terms of math is that it turns out the speed of a wave, or the speed of light in this case, is equal to the frequency of the wave times its wavelength. Big equation. This is the main wave equation that we're going to talk about. I've written it for light, but it's true for all waves. More in general, the velocity of a wave is the frequency of the wave times its wavelength. If it's light, then we call the velocity c. If it's water, then it's just v, whatever it is. And this makes sense. Given a certain velocity, so the v is a number, and it doesn't change. If I increase f, I have to decrease lambda to keep the number the same. So the bigger the f, the smaller the lambda. Smaller the f, the bigger the lambda. So this is our first big equation. First big relationship between the physical characteristics. And again, just as usual, I go through the theory before I do a whole bunch of examples where we see how to use these things. But for now, just keep this in mind. This is our first big relationship. But this is not all we want to know. It turns out sometimes there are other, how should I put it, characteristics, other ways of thinking about these things. And one of them is called the period of oscillation. So the period of oscillation, it's got the variable capital T. Okay. And what the period of oscillation is how long does it take to make one oscillation? So this is very, very similar to frequency. Frequency is how many oscillations are there in 1 second. Period is how long is it? How many seconds are there in one oscillation? Okay, so similar, but kind of the opposite of each other. In one sense, the frequency, you're going to measure 1 second of time and you're going to count how many waves there are. In the period of oscillation, you're going to watch the wave and you're going to start your timer and you're going to see how long does it take before you get the next wave. So for one full oscillation, how many seconds go by? And so the equation for period of oscillation, by the way, the unit is just seconds, because it's how long, how much time does it take to do an oscillation? Well, period is just 1 over frequency. Very nice. So if you know the frequency, just take the inverse, the reciprocal, 1 over the frequency, and that gives you the period. So that's nice. That's another thing you may want to know. What else is there? Well, it turns out that a lot of times when we go to mathematically predict what's going to happen with waves, for instance, let's say I want to know something about ocean waves, and I want to predict where will the highest point of a wave be in 2 hours. What's going to be the highest amplitude or the height of a wave at a certain time? Something like this. I want to know about the wave and then predict what will happen in the future, or what would I expect to see if this is true. Now, the problem is in doing these things, which we can do, and I'll show you the equation to do it, the problem is that the numbers are not that fun. Here's the equation. So this is the equation of a wave. Here we go. The equation of a wave goes like this. Y is equal to A sine of, let's say, how do I want to do this? 2 pi over lambda times x minus 2 pi f t. Okay, so let me explain what this says. First of all, what this equation is this y, the thing you're solving for, is the height of the wave at a certain position and time. Okay, so you have the ocean, you're sitting there on the beach, you're looking out at the Gulf of Mexico, and you see all the waves, and you say, okay, I've watched these waves enough, I've figured out the frequency of the waves, I've figured out the wavelength of the waves. I want to know if I wait an hour and pretend we don't have changing the moon isn't there to give us the changing tides and all that kind of stuff. It's constant waves all the time, just to make this an easier analysis. So I want to know if I look over there 10 feet away in 2 hours, what will the wave's height be? How high will the wave be? Or how high will the wave be, or how high was the wave 5 seconds ago over at that location? If I get enough information by studying the waves for a little bit, I'll know its frequency, I'll know its wavelength, and I can use this equation to predict the height of a wave at any location in the Gulf of Mexico or at any time. And so this X and this T are the chosen position and time. Okay, so I would say X, that's going to be 10 meters away. So I would choose an X, 10. And then T is the time I want to figure out. So let's say 20 seconds from now. So T would be 20 seconds. So I choose the X and I choose the T to plug into this equation to get my answer out of it. Okay. In order to do it, we need to know a few things. Of course, we need to know this A, we need to know the lambda, and we need to know the F. So what's the A? The A is called the amplitude of the wave. And the A is the highest the wave will ever be, the tallest. Okay, so if you have water waves going on, you're there watching at the beach, and you look at the maximum height of the wave, that number, whatever that number is your amplitude. Now, obviously, if you look at a wave, the amplitude goes up and then it goes down and then it goes up. So this, when it's at its highest point, that's your A. But notice, a little bit of time later, now you're here, you're at a different height. And that's what the Y would say. The Y for this graph is what is the height of the wave at certain times. At certain times, it's at the maximum height, which we call the amplitude, the A, but at other times, it's at other heights. And so this equation I just created is an equation which allows us to figure out what height will be at certain times. Well, I need to know the maximum height first. How high will it possibly get? And that's what the A is. Right, then we have the sine. Well, that's just the trig function, sine of two terms. First term, 2 pi lambda times x. Remember, x is just, I'm going to feed this equation the number for x based on what it is I'm trying to find out. I want to know 10 meters away, what will the height of the wave be? So I plug 10 in for x. So that's something I give it. The lambda, well, that's the wavelength of the particular waves we're studying. So that's something about the wave itself. The wave has a wavelength of 0.5 meters. So I would have to plug in 0.5 for this lambda. And an F, that's the frequency of the wave. So wavelength and frequency are things I have to get from the wave itself. Those are the things that the wave is made of. And so I can't make these numbers up. I have to be given these numbers. The X and the T are the things I get to choose freely based on what answer I'm trying to get. But there we go. There's my equation. I want to know the height of a wave at a particular time in a particular place. What do I need? I need the maximum height of the waves. I need the wavelength, and I need the frequency. But no, I mean, you could look at this equation and say, man, that's really messy. 2 pi over lambda and 2 pi f. I don't like that stuff. So what physicists did is they said, look, every time we do this equation, we always have to do this 2 pi over lambda business. So why don't we just come up with something new instead of wavelength? Because although I use the wavelength, I use the wavelength as 2 pi over lambda. I don't just use lambda by itself. So let's come up with something which is 2 pi over lambda and call that thing something else. So I'm just going to rename this thing 2 pi over lambda, and I call it k, little k. And what is little k? It's called the wave number. Okay. The only reason to do this is simply so that when I write down these equations, I don't have to keep writing down the 2 pi business. It's just a shortcut. It's a way to make the equation look prettier. So you replace 2 pi over lambda with the letter k. But k is, you still have to calculate 2 pi over lambda. You're not getting rid of it. You're just not writing it down. You're only writing down a k. And then the 2 pi f, same kind of a thing. Instead of writing 2 pi f, we're going to write down a different letter. This letter is the Greek letter omega. It looks like a curly W. And this is called the angular frequency. Okay, so it's still like a frequency, but instead of it being the normal linear frequency, blah, blah, blah hertz, this is the angular frequency. So this is going to be in radians as a unit. But how do you get the angular frequency? You just take the frequency and you multiply by 2 pi. That's it. And so with these two things, we rewrite the equation y is a sine kx minus omega t. And look how much prettier that is. A lot less complicated looking. It's the same thing, because when we go plug numbers into this, I have to calculate what k is. So I have to do 2 pi over lambda. And for omega, I have to plug in 2 pi f. But at least when I write down the equation, it looks pretty, and I don't have to write down that many things. So that's going to be the form of the equation we use. And no, wave number and angular frequency. K, what is wave number? It's basically like the wavelength, but it's actually 1 over the wavelength, but it's similar to the wavelength, okay? So in my brain, I always associate wave number with wavelength, and of course, angular frequency is frequency. It's just a little different. It's not exactly the same number. You have to do some stuff to it, but when you see wave number, you can think something like wavelength. So there we go. There's our big equation of a wave. And as I said, with this, I can give you a certain wave. I could say, okay, you have a water wave whose maximum height is 4 meters. It's got a wavelength of, let's say 3 meters and a frequency of 20 hertz. Calculate or first of all, write down the equation for this wave. And secondly, calculate the height at t equals 45 seconds. That's how you could use this. Okay. So I would give you the information for the wave, the characteristics, and then you'd have to plug those characteristics into this equation. So that's the next big thing. First thing, the big relationship between speed of light or speed of a wave, frequency, and wavelength, the 3 characteristics of a wave, and then the equation of a wave, the mathematical representation of a wave as it moves through whatever medium it's in. The last thing I'll show is, well, I just have 2 new characteristics sitting here. So why don't I try to create another relationship like the speed of a wave is frequency times wavelength, but using these 2 things instead. Maybe that's useful. So how do I do it? Well, what I want is V is F times lambda, right? But I don't want to use F, I don't want to use lambda, I want to use omegas and Ks instead. So let's look at the K one first, 2 pi over lambda equals K. And let me solve this for lambda. So how do I solve for lambda? Multiply lambda to both sides. That cancels here. And then I divide the K over to the other side. So this tells me lambda is 2 pi over K. And then the same for the frequency. I know omega is 2 pi f. So I want to solve this for f. I got to bring the 2 pi over to the other side. So f is omega over 2 pi. And now all I have to do is take these two things and plug them in to that equation right there. And what do I get? V is frequency, but frequency is omega over 2 pi times wavelength. Wavelength is 2 pi over k. And now we see 2 pi cancels 2 pi, and we're left with the main equation, V is omega over k. So there's a second relationship between the three characteristics. Okay? The main one, frequency times wavelength is velocity, that's the main one. Because that uses the stuff we're used to. Frequency and wavelength, those are natural characteristics. However, because we're going to be messing with this equation for a wave where we usually have to know omega and k, we may not know the frequency and the wavelength. We may know omega and k instead. Well, if that's the case, then we could use the relationship V is omega over k. It's the same thing. So here are three big equations. Okay. And then it's with these equations, the first part of this analysis of light that we're going to work on. We're going to do some examples with them. We're given a wave. It may be light, it may be a water wave, it may be a sound wave, whatever it is. This wave is going to have some physical characteristics associated with it, like the frequency of the wave, the speed of the wave, the wavelength. And we want to try to do some analysis. Maybe I'll say sound wave, or you have a wave. It's got a frequency of 5 times 10 to the third and a wavelength of 0.02. What is the speed of this wave? Okay. Or write down the equation for a wave whose speed is 350 meters per second and whose wavelength is 0.1 meters. And so you would have to write down the equation of the wave. These are the types of questions we're going to be doing at first. Okay. From here, after we're done with this, or doing those types of problems, we're going to start getting into some more interesting aspects of light. Things like what's called polarization. Polarization is an important effect of light, although we can't see it. Like our eyes cannot tell the difference between light that's polarized and light that's not polarized. But we do make use of the polarization in doing things. For instance, you've probably heard the word polarized before in terms of sunglasses, polarized sunglasses. Well, the reason they're polarized is because they design the lens of the glasses to block out light, which is polarized in a certain way. And that helps make sunglasses work better than if all you did was tint some glass and make it darker. But there's also other places where polarization comes into effect. For instance, 3D movies, the way those 3D goggles work is making use of polarization. So we're going to talk about polarization and that kind of stuff. And then we're going to get into things like lenses and mirrors and things like that, and how images are formed. So that's kind of the roadmap where we're heading. We'll first deal with the actual physical characteristics of waves. We'll do some examples next class, and then start into the more interesting stuff after. Any questions about what we talked about today?
I actually got a question. So when I saw you was doing the substitution method, like I understand what you meant by substituting 2 pi over lambda and putting it as k to simplify the equation.
Yeah.
When you went, I got confused when you were saying you do when you did velocity and K, like what actually is K? I don't know if I'm
Yeah.
off.
Yeah. What physically is K? That's a difficult question. That's not, we can see wavelength. That makes sense in our mind, right? The wave is moving up and down as it travels towards the beach. And you say, okay, from this distance to this distance is one full wave. K, wave number, if we think about what it is, it's, forget about the 2 pi. The 2 pi is just a number. So it's 1 divided by the wavelength. Well, let's look at what we said for frequency and period, because period is similar, right? Frequency is how many oscillations are there in 1 second. And then we made this other thing called period, which is how long does it take to do one oscillation? And that was 1 over the frequency. So period is like wavelength. It's, instead of how far does the wave go in one oscillation, it's how much time does it take for one oscillation. So in our minds, period and wavelength are similar. Only one has to do with time, one has to do with distance. And in frequency was, we're going to look at 1 second and see how many oscillations there are. So that means K, being 1 divided by the wavelength, is like frequency, only in terms of space. So you would say, okay, let's look in 1 meter. So from this point to this point is 1 meter, and I'm going to look at how many times or how many waves there are in that 1 meter section. So there may be, 2.4 waves in 1 meter. Whereas the wave, so let's do a real wavelength. Let's say a wavelength of 0.3. Okay, so a wavelength of 0.3 would mean that you could go 0.3 meters in doing one oscillation. K would be 1 over 0.3, which is 3.333. That means if you look in 1 meter, from this point to this point is 1 meter, and you count how many full waves there are, you get 3.33 waves per meter. Okay, so that's the difference. It's weirder to think about, but the wavelength is how many, our wavelength is how far does the wave have to go to complete one oscillation. K is if I look 1 meter, how many complete oscillations are there in that 1 meter space? Okay, so that's kind of a similarity between period and frequency. Frequency, how many waves, how many oscillations are there in 1 second? Period, how long do I have to wait for one oscillation? Okay, so does that make a little more sense?
Yes, sir.
Good, perfect. Any other questions? All right, well, that's all I have for today. We did a bunch of theory this time, but next time we'll do examples. And I think the examples will certainly help to set all this stuff better into our minds. We actually do the math, we get some answers, and we see how to use this stuff. For now, I just wanted to make sure we have all the equations we need, and then we'll work on some problems next time. So that's what we'll do. And in the meantime, I hope you enjoy the rest of your day. I will see you on Wednesday.
Have a nice day.
All right, you too. Thank you.